Okay, we're on section 5.2. All right, at the end of the 1800s, the physics that was available at the time said that particles that were moving should give off energy, which meant that electrons should have been losing energy as they were moving outside the nucleus, and that matter should collapse, okay? And obviously, this isn't what was happening. And there was a German physicist by the name of Max Planck. And what he did in 1900 was he proposed that energy could be shown to behave like particles, as little packets of energy that he called quanta. He called this the quantum theory, and he developed an equation to measure the energy associated with these packets or quantum. The equation is E equals hv. E is energy, V is the frequency, and then H is a constant, 6.626 times 10 to the negative 34 joules times second. This is called Planck's constant. You would never memorize this. This is something that would always be given to you, okay? And energy can be absorbed or given off in whole numbers of quanta. So it's kind of like if you think of, you've got a bag of marbles, I can only pick out whole number quantities of marbles. I can't pick out fractional numbers. So the same concept applies with energy being absorbed and emitted. So I think that's all we're going to talk about from this page. Let's take a look at the next page. His theory wasn't really taken seriously. It wasn't until Albert Einstein wrote some papers and he used quantum theory to explain the photoelectric effect. That physicists couldn't explain the photoelectric effect until Albert Einstein used the quantum theory. So basically what was said was that because Albert Einstein applied the quantum theory, soon this theory gained wide acceptance. In 1921, Einstein won the Nobel Prize in Physics for his explanation of the photoelectric effect. So let me explain what this concept quantized means. Quantized means that you have distinct energy levels. It's kind of like if I decided to take the stairs down to the first floor, each stair has a distinct level, okay? So stairs are quantized. If I took a slide down, a slide is not quantized. Do you see the difference? Okay? And let's move on to the Bohr model of the atom, okay? Okay, so Bohr, let's go to the next page. Bohr used the concept of quantization as it applies to electrons existing in distinct energy levels outside the nucleus. He came to this concept by looking at something called a bright line spectrum, okay? So if I take a lamp that is filled with, let's say, helium or hydrogen, and I look at it through a hand spectroscope, I'm going to see distinct bands of color appearing at different wavelengths. These distinct bands of color actually come from electrons that absorbed energy and they jumped to a higher energy level. And as they come down, they emit these bands of color. So each one of these leads to the concept that electrons must exist in distinct energy levels outside the nucleus, and this is the reason why matter doesn't collapse. So if I come down here and I take a look at Bohr's postulates for electrons and where they exist, what he says is if I'm looking at the simplest atom, which he studied called the hydrogen atom, there are certain energy levels which are stationary, and in those energy levels, that is where the electrons are allowed to exist. And there are no other that exist. So for every energy level, we label them with an N, and he called these quantum numbers. Now, we are not going to go into the details of quantum numbers here. We're just going to focus on the N's. So the lowest N, or the lowest energy state, is called the ground state, and we would call it N equals 1. And as you get further out from there, we get larger orbits or larger energies like N equals 2, 3, 4, and etc. And we call these the excited states. Now, what we're going to do is we're going to look at your periodic table, the one that I gave you, this one, and we're going to label these with the N's, okay? So we're going to start with hydrogen on the left-hand side. So I want you to write to the left of hydrogen, N equals 1. And then when we come down to lithium, this would be N equals 2. And then sodium would be N equals 3. And then potassium is N equals 4. And then you get the idea. Rubidium would be N equals 5. Cesium is N equals 6. And then after that, francium would be N equals 7. And that's as far as you're going to go. Okay? So these N's, or energy levels, correspond to the rows or the periods on the periodic table, okay? N equals 1 would be the lowest energy, N equals 7 would be the highest energy, okay? These are the energy levels outside of the nucleus where electrons can exist. Okay, now, as long as the electrons move between these allowed energy levels, they absorb energy to move up to a higher energy level, and then they release it as they move back down. Then we don't have matter that collapses. So I think that's all I'm going to highlight here on this page. Let's take a look at the next page. Let's go to here. Okay, so here this figure is giving you an idea of what I was just talking about. So here you'll notice that the green sphere is my nucleus. So N equals 1 would be the first energy level. That would be what you wrote next to hydrogen. N equals 2 is a little bit further out. And then N equals 3 is even further, and it keeps going and going, okay? So when you have an electron, which is this little tiny blue dot right here, an electron can jump to a higher energy level. So here this electron is going from N equals 2 to N equals 3, and in order to jump, it has to absorb energy. So if I shine light at a sample of matter, that means the electrons in that sample of matter can absorb energy, and then they won't stay in that higher energy level forever. They have to come down. So as they come down, we call this relaxing. So moving from N equals 3 to N equals 2 is relaxing. And as it does that, it emits a wavelength of light. So that's what this little red squiggly line is here. And every electron that transitions or moves between energy levels will emit a different band of color, okay, which will correspond to the energy that it had absorbed, all right? So N equals 2 for this particular electron would be called the ground state. That's where it starts. And then N equals 3 would be its excited state. Okay, so moving from a lower energy level to a higher energy level is absorbing energy. Moving from a higher energy level to a lower energy level is releasing energy. Okay? Okay. Can I move this down? Yeah? All right. All right, every single element has a unique emission spectrum. So here you can see hydrogen, mercury, and neon are compared, okay? These are like fingerprints of an element. So I can identify what element I have based upon the emission spectrum that you see. Okay. Now, the emission spectrum, these are called discontinuous because each band of color is separated by a black region. Okay. If I look at white light through a hand spectroscope, you would see a rainbow, which would look something like this, of continuous color with no interruptions, and that would be known as continuous. So white light will produce a rainbow when you look at it through a hand spectroscope, and this is known as a continuous spectrum. Okay. Okay, let's take a look at the next page. On the next page, they gave particular names to the electron transitions in the hydrogen atom. So let me explain. Here you can see that all of these transitions are coming down to n equals 1. So when the electrons all move down to the n equals 1 level, this is called the Lyman series. When they all come down to the n equals 2 level, this is called the Balmer series. And then coming down to n equals 3 is called the Paschen series. And then coming down to n equals 4 is called the Brackett series. Now, depending upon which n you're coming down from, or coming down to, I should say, that determines whether or not you're going to see it. So the Balmer series is in the visible region, so you can see those with the naked eye. You would still be looking through a hand spectroscope. The Paschen series, these actually appear in the infrared region. You cannot see those. The Lyman series appear in the ultraviolet region. You also cannot see those. Okay? What are they doing out there to the door? Okay, let's go to this next page. Did I remove this from your book, or is it still there? Yes, awesome. Okay, so we don't have to talk about it. All right, so do you